In this lesson we'll examine upper winds. In particular, we'll see how they are generated, the factors that control their velocity, and also how we can identify the bands of very fast upper winds, which we call jet streams. With an understanding of upper winds and jet streams, we can better prepare for our flying. But more importantly, we'll be able to recognize and avoid potentially dangerous conditions. Looking at the formula for the velocity of a wind, we can see an important relationship. The main variable relating to upper flow, as opposed to surface flow, is the density of the air. In the upper atmosphere, the density is significantly reduced. From the formula, it's plain to see that a decreasing density will cause an increase in speed. Therefore, the higher we go in the atmosphere, the lower the density, and the greater the speed of the wind. This is generally true up to the tropopause level. As a result, we should expect to find our fastest winds just beneath the tropopause. The angular velocity of rotation of the Earth and the latitude components of the formula are almost constant with altitude and will be ignored within this lesson. The other main element of the formula is the pressure gradient force. As with surface winds, the greater the pressure gradient force, the greater the speed of the wind. We've seen in earlier lessons what factors control surface pressure. But what is it that controls upper air pressures, and therefore upper air pressure gradient forces? More importantly, why do we have varying pressures in the upper atmosphere? There is a simple explanation: the varying temperature between different air masses. We saw how varying temperatures influenced upper air pressure in the lesson on pressure. However, let's just recap the fundamental points. Cold air, as we know, is denser and thus heavier than warm air. It tends to increase the pressure lapse rate. In other words, it causes pressure to fall more quickly with altitude. As a result, at any given altitude in a cold air mass, the pressure would be lower than at the same altitude in warm air. These two diagrams demonstrate the principle very well. Notice that at 30,000 feet, the pressure is lower above the cold air than at 30,000 feet above the warm air. Now we have a pressure variation at 30,000 feet, just like we had pressure variations on the surface. It's now clear that cold air and warm air cause variations in upper air pressure. Above cold air there should be low pressure, and above warm air there should be high pressure. To understand upper winds and upper air pressure, all we have to do is find warm and cold air. This is best done using contour charts. These charts are quite complicated, but let's just consider their essential elements. The contour chart is simply a plot of the heights of a pressure surface, or pressure level, above a particular point. In the diagram, we can see varying heights of the 300 hectopascal pressure level. A contour chart will simply plot the height at which this pressure is found. You can see that in cold air, the 300 hectopascal pressure surface is found lower than it would be in warm air. If we now look at a very basic contour chart, we can identify areas where the 300 hectopascal level is lower than elsewhere. This would suggest cold air. Conversely, there is an area where the 300 hectopascal pressure level is found much higher than elsewhere, shown here. This is indicative of warm air. Now we know where warm and cold air is located, we can infer what the upper air pressure would be. Earlier we said that above cold air we would expect a low pressure, and above warm air a higher pressure. This means that wherever we find low-value contours, we know this will be due to cold air, and we'll therefore expect a low pressure in the upper atmosphere. Alternatively, wherever we find high-value contours, we'll know this will be due to warm air, and therefore we'll expect a high pressure in the upper atmosphere. Think of a surface pressure chart and how the winds blow in relation to the isobars around lows and highs. Let's now examine this chart in relation to upper wind direction and speed. We already know that the pressure gradient force acts from an area of high pressure to an area of low pressure, as shown. As a result, the air will want to flow towards the lower pressure. But as we've learnt, the moment air moves, the geostrophic force, or Coriolis force, acts on the airflow. In the northern hemisphere, this force acts 90 degrees to the right of the wind direction, and as a result, the air flows parallel to the contours, as shown here. This leads to an adaptation of Ballot's law, but this time modified for temperature. With your back to the upper wind in the northern hemisphere, the cold air is to your left. This is because the cold air creates a low pressure in the upper atmosphere. In the southern hemisphere, remember, the Coriolis force acts 90 degrees to the left of the wind direction. As a result, with your back to the upper wind, the cold air is on your right. Using these very basic laws will help you to determine the direction of any upper winds. Let's look at a broad view of the Earth and analyse where we find warm and cold air. Generally, we can say that equatorial regions are warmer than polar regions. Using Ballot's law for the upper atmosphere in the northern hemisphere, we can see that the general upper wind will be westerly. With your back to the upper wind, the cold air at the North Pole is to the left. Looking at the southern hemisphere again, we can see the general upper wind pattern is also westerly. With your back to the upper wind, the cold air at the South Pole is now on your right. The speed of these upper winds in either hemisphere increases slightly with latitude, from approximately 20 knots at about 20 degrees latitude to about 40 knots at 60 degrees latitude. However, notice an area near the equator where the general upper wind pattern is easterly. Do these winds obey the laws we've learnt? They do. But to understand why, let's examine them in a little more detail. Here we have a diagram concentrating on the area just above the equator, up to 20 degrees latitude. We learnt from the lesson on temperature that in June and July, which is the northern hemisphere summer, the area at approximately 23.5 degrees north is receiving greater amounts of solar radiation than the equator. This would mean that the equator is relatively cooler than 23.5 degrees north. If the law in the northern hemisphere says that with your back to the upper wind the cold air must be to the left, then the upper wind must be easterly. Let's look at the same zone, but in the southern hemisphere. In December through January, the southern hemisphere summer, the area at approximately 23.5 degrees south is receiving greater amounts of solar radiation than the equator. This would mean that the equator at this time is relatively cooler than 23.5 degrees south. If the law in the southern hemisphere says that with your back to the upper wind the cold air must be to your right, then the upper wind must be easterly. Remember, though, that these easterlies would only be apparent in their respective hemispheres' summer. However, in the upper atmosphere we can find very narrow, fast-moving currents of air. If the upper winds exceed 60 knots, then these winds are called jet streams. What causes these winds to be faster than normal? Remember that it was temperature variation that caused upper air pressure variation. Therefore, in order to create a strong upper wind, we would need a very strong temperature gradient to exist. In fact, if we look around the Earth and locate areas where cold air and warm air lie adjacent to each other, then we'll most probably find jet streams. Shown here is a typical jet stream, highlighting its approximate dimensions. Shown here is an upper air spot wind and temperature chart for flight level 340, approximately 34,000 feet above mean sea level. We can decode the wind speed and direction in the same way we did for the surface winds. The thick black triangles represent 50 knots, the thin black lines 10 knots, and the half-length black lines only 5 knots. Remember that a jet stream has a wind speed in excess of 60 knots. Let's see if we can identify a possible jet stream by highlighting all those locations which show a speed in excess of 60 knots. As you can see, the shape and size of the jet stream is slowly becoming apparent. The number next to each location is the temperature of the air in negative values. If this map is for the northern hemisphere, then we should be able to see a stark temperature difference either side of the jet, with the colder of the air masses being on the left. These charts are primarily used for something else, though, namely flight planning. Looking at the diagram, we can show a route from London to Lisbon. We can use the spot wind values adjacent to the track line to calculate an average wind component. This data can then be used to calculate flight times and trip fuel. If we look at a jet stream in cross-section, we can see the thin black lines. These are isotachs, which join lines of equal speed. Notice that the core is identified by the highest isotach values. If we look at the core, notice that it's found just beneath the tropopause and in the warmer of the air masses. The point at which the isotachs are closest together marks the greatest change in speed. Therefore, the potential location of clear air turbulence, or CAT. The side of the jet where the isotachs are closest is the side facing the cold air. This is where the temperature gradient, and therefore the pressure gradient, is the greatest. The locations of these CAT areas are important since they can represent a significant hazard to aviation. As a result, these jet streams and their associated CAT will be forecast and shown on weather briefing charts. The decoding and understanding of these charts is explained in the flight briefing section of this CD-ROM. Let's now list the different jet streams we find across the Earth and explain their formation.